And some of you may already notice that I didn't actually talk too much after the class. Don't misunderstand that. I'm a social person. I talk a lot. I talk fast. But I need to actually keep talking 6 hours tomorrow, so that's why I have to save some voices, okay, today. So after the introduction this morning, I actually would like to go ahead with the computing method instead of model construction, because the whole procedure, okay, including model construction, sensitivity analysis, identifiability analysis, and model selection, that will be a whole procedure, okay, which will be covered tomorrow. So now let's switch the gear, okay, a little bit. Computing method. So we have talked about some commonly used tools in mathematical modeling, okay, including the ODE model, PDE model, SDE, agent-based model, and Monte Carlo, Markov chain Monte Carlo, and optimization. We already sort of know what's ODE, okay, and the PDE we already know. PDE can actually take the spatial difference into consideration. That's one advantage of PDE. SDE, we know that it includes the randomness or stochasticity into the model. Agent-based model is more like a stochastic simulation tool, which Catherine from Canada will actually spend the whole day with you, with Tom Kepler, actually, talk about the agent-based model. So I will not talk about that either today or tomorrow. Markov chain is more like a conditional probability model. For now, probably we don't care about what it is. And but we will actually talk about optimization, which is actually of extreme importance, okay, to modeling. I'm gonna explain why. And now we definitely cannot actually cover all these different tools and how to numerically deal with them. What we can do actually is I selected the ODE, PDE, and some stochastic simulation algorithm plus the optimization algorithm. Okay. For the rest topics, if are interesting, Wednesday that's about agent-based modeling, and unfortunately we don't have anybody to cover the MCMC. Okay, although it's a very important tool. In general, okay, when we use these mathematical models, okay, or modeling tools, there are two categories of problems we want to solve. One is called the forward problem. The other one is called the inverse problem. So actually this morning we already talked about the forward problem. We mentioned that if we give a parameter value, and if we also give a initial condition, for example, 100, then we solve the ODE to get the complete trajectory, of course. Depends on what model you're considering. If it's an exponential growth model, you want to actually know every detail about this curve, okay? So that's called forward problem, okay? Which means giving parameter values, giving initial conditions, then I predict what happened afterward, okay? So it's called forward in time, okay? So, however, inverse problem does not mean that I want to solve this problem backward in time, okay? That's not the meaning of the inverse problem. Inverse problem is that I don't know the parameter value, okay? However, now I have data. With noise, right? I have data. Now I want to infer the value of this parameter from data. Okay, that's called the inverse problem. Okay, so clear? Now, there are many other related problems, okay? For example, the sensitivity, identifiability, convergence, bifurcation analysis. Unfortunately, we don't have time to talk about all of them, but we will cover the most important and basic one, okay, sensitivity and identifiability. So that actually is directly related to your model structure. So now, let's actually spend like 5 minutes to finish the first grade undergrad course of calculus, okay, just 2 slides. One slide is derivative, okay, we talked about this morning, right? We say that the derivative is actually the change per unit time, or equivalently, that's the rate, or equivalently, that's the slope of the tangent line, okay? So they are the same thing if you just look at this plot, okay? Giving a time interval, you look at the, let me see, where I can use it. Okay, you look at this distance. This is a change, okay? This change divided by the time interval, that's where you get the derivative. Okay, so usually a lecturer will need like 10 courses to explain this idea, but we finished it in like a half minute, and I'm gonna spend another half minute to explain the idea of integration, okay? Integration comes from the problem that we want to calculate the area under the curve, okay? So this is my curve. The blue curve is my curve, okay? And if this is a straight line, okay, the area under the curve is easy to calculate, right? But now if it's an arbitrary shape, okay, how we do the calculation? Calculate the area under the curve. So the idea actually is also simple. Since I cannot directly calculate the area under the curve, let's divide that into small pieces, okay? And within each interval, okay, I use a rectangular bar to approximate the area under the curve within this interval, okay? So of course, there's a approximation error, right? Here, we actually didn't cover that part, that area, okay? But it's okay. Why? If we keep dividing this into smaller and smaller interval, the approximation will be better and better, right? So eventually, okay, I can calculate the area under the curve using the summation of the area of all the bars, right? And once we have enough bars, or divided the whole interval into much smaller intervals, okay, the approximation actually will be very accurate. Okay, so you don't need to worry about it. Of course, all the numerical algorithms, they have errors, okay? If the error is very small, then we don't need to actually worry about it. So that will be the idea of integration. So the notation will be, I don't know how to call it, okay? Doesn't matter. So you have integration operator. This means the integration operator. And this is a starting point, this is end point, okay? Which means from here to here, okay? And this x is your blue curve. And this just gives you the area under the curve. Okay, half minutes, finish the calculus course, okay? So now, in the first section, I want to talk about how to solve ODE models, okay? That's what we just talked about. Give the parameter value, give the initial condition, how we actually numerically solve to get the whole trajectory, okay? Again, here's the terminology we should get familiar with. And we're gonna use this kind of terminology tomorrow, okay? So we know that D is the derivative, okay? Means the differentiation, okay, operation. X is a dependent variable or state variable. T is an independent variable or tan, simply call it. And we can write it this way. These two are equivalent, okay? And T, again, X, theta. Here, I use theta to denote the parameter, all the parameters. So one model can have more than one parameters, okay? One model can have 10 parameters. If you're talking about a network model, you probably have thousands of parameters, okay? So this theta doesn't mean it's one-dimensional, okay? It can be 1,000 dimensional, okay? F here is actually an arbitrary function of T, X, and theta. So that will be the general structure of ODE model. So now if we need to solve ODE, we also need to specify two other things, okay? The first one is time window of interest. So from T0 to T1. So why can't we go to infinity? Instead of from t0 to t1, we can go from t0 to infinity, right? But usually we don't bother to do that, okay? First, in experiments, you cannot actually observe things, okay, after infinite time, okay? So that's too long. Nobody gonna fund you, okay, to do that. Secondly, even if we want to understand the system behavior at the infinite time, we have other method, okay, which we also will talk about, which is called usually called steady state, okay. So there's alternative methods to deal with that, so you don't have to worry about it for now. Initial condition, of course, we need to know we are starting with 1,000 cells or 10,000 cells, okay, in my culture, okay. So that will give you a different, curves, trajectories, okay. So of course, like I mentioned before, theta has to be specified, okay. If you don't know theta, you cannot solve the ODE, okay. So actually, you need to specify three things: theta, t0, t1, and the initial condition. Then you can solve ODE, okay. This is a forward problem. Now, let's look at the necessity of a numerical solution to ODEs. So if we consider this very simple exponential growth model, okay, we talked about this morning, right? I just replace the row with a 2, okay, of specific number. Then we have an analytic solution like this, which actually looks simple, okay. This one is simple. However, if I just somehow manipulate this equation a little bit, put a square root of x and add 1 over x here, so what's the solution? Can you get a closed form solution or anyway? Actually, you can. I tried this one using Mathematica. Okay, Mathematica can do, the package in Mathematica actually can do the symbolic computing. Okay, and the results actually, the results actually is 3 lines long. Okay, you don't want to bother to use that long solution. Okay, I give you lots of struggling. Okay, so that's why people actually use a numerical solution. Okay. So for this simple, this is actually also a simple, ODE model. So, but even for this one, okay, you probably will consider numerical solution, okay. However, numerical solution is a discrete approximation, okay, to the continuous solution. Remember, if I have we talked about this morning, okay, NT, okay, is continuous, okay. So when we solve it, okay, we cannot actually calculate every single point on that trajectory. What's the reason? So if I have a curve like this, how many points are there on this curve? Infinite number, right? Because they are continuous. You can divide this into smaller interval, and you still get 1 point, okay? That's why when we solve the ODE, okay, we only solve at a certain distance. For example, if I start from here, I'm gonna jump a little bit, then I get a predicted value here, and then I jump to here, then jump to here, okay. So that's what I mean by discrete approximation, okay. So you will not get actually every point, okay. It's not possible. However, if you are really interested in this point, which is not covered by any of the points in the solution, there's a way, okay, to calculate this back. Okay, the algorithm actually will handle that, so you don't have to worry about, this sort of problem. Now let's actually look at how to actually numerically solve ODE. Okay, so let's start from the equation. Okay, this is our general ODE equation, and remember, when we derive the derivative, we actually start from this approximation, okay? We start from the difference divided by the interval, right? Now, when we solve it, we actually go back to this approximation, okay? So instead of the exact derivative at 1 point, okay, we go back to this approximation. Now, if I plug in this approximation into the left-hand side, you will get this equation, right? Okay. So next step, we just multiply delta t at both sides and move xt back to the right-hand side. So what are we doing? This morning, we're actually doing, the opposite direction, right? We start from here and go back to this equation and then go back to, and eventually we get this equation, right? So when we solve it, we actually, follow a opposite direction, okay? So once we get to here, then one good thing you can tell is that if I know the value of x at time t, okay, and also if I know the time interval I'm looking at, then I can actually predict the value, approximate value at t plus delta t. Okay, so that's the idea. So once I know this one, I can predict the value here. Once I know this number, then I can use this formula again and predict the value after 2 delta t and after another delta t. Okay, so that's a very famous Euler method. Okay, so every numerical algorithm book will talk about this Euler method. Okay, but the basic idea is actually extremely simple. You start from one point, predict the next value, okay, and then predict the next one. So what's the immediate problem you can see from this slide? So blue curve is my true trajectory. However, my Euler method is shooting away, right, from the true trajectory. So that's something called numerical error, okay? Remember, when you use numerical algorithm, okay, you always get a numerical error. But again, if a numerical error is small, then you don't need to worry about it. And algorithm actually has many strategies to control that numerical error, okay? So anyway, I have to say Euler method is not a very accurate algorithm, okay? As you can tell from the plot. That's why people also derive the so-called Runge-Kutta method. The Runge-Kutta method, okay, this is actually a much more accurate, okay, algorithm than the Euler method. So if you look at this equation, okay, now again, we're trying to predict approximate, okay, the value of x at t plus delta t from the value of xt, okay. But what changed is here, okay. Instead of f multiplied delta t, I have a little bit more, sophisticated term here. So it's a k1 plus k2 plus k3 plus k4, okay. So if you look at k1 actually is exact same term as in the Euler method, right? And k2, actually I use what I calculated, okay, for k1 here. Plugged it in and update my prediction. Then I use this prediction, update this prediction again, I get k3. And finally, I use this prediction to update k4. So what I'm talking about right now is a little bit difficult to understand, but if you go to this slide, okay, this will tell you k1 is actually the increment based on the slope at t. We know slope is actually the derivative at t, okay? Slope, derivative, they're the same thing, okay? We have talked about this for quite a few times. So again, k2 is increment based on slope at t plus half of delta t using xt plus half of k1. Similar for k3 and similar for k4. So if you're saying that I still don't know what you're talking about, okay, here's a slide. That's why I have this slide, okay. So remember, when we start from k1, okay, k1 is actually the slope at time t, okay, product of the slope with delta t, okay. k1 is equal to the slope, okay, at t, at time t, okay, multiply delta t. Okay, so here is the slope. This is a tangent line, okay. The slope of this tangent line is what you saw here in K1. So I start from K1, and then I predict what the value of this curve will be at the middle, in the middle, okay? That's why you get K2, okay? And at K2, I calculated this slope again and use this slope to calculate K3. So these two lines, they are parallel, okay? And the reason I do this is because I suspect if I only use the slope here, the results may not be correct enough, accurate enough. Then I do some correction, okay? Using this prediction, do some correction. So I in hope that to improve the accuracy. Same thing here. When I get the slope here, I'm not sure whether it's accurate enough. So I do a correction again. That's how I calculate K3. And finally, I use the correction again to actually calculate K4. So these two lines are parallel because they're using the same slope. Okay, so that's the idea behind the Runge-Kutta method. Okay, you predict once, but you improve it by correction. Okay. So if you go back to here, you will see that's what I'm talking about. Okay, you do the correction here, you do the correction here. So eventually you add them together, and mathematically actually you can prove that the numerical error actually will become much smaller. Okay.
But you could make it better if you do 1/3 or 1/4, right?
That's a good question. So actually I can a little bit extend that question. Means why don't we just use K1, K4, or why don't we just use K2, K3? So when people derive this kind of formula, okay, eventually they will derive a term to approximate the numerical error. So this turned out to be a best balance, okay, and that's why you put a 2 here, and divide by 6. So there's actually a optimal balance, okay, between these 4 terms. Okay. Any question? Good. Okay. Oh, no question could be good, could be bad. Okay. So I hope it's not the latter one. Okay. So. So if after we derive the Runge-Kutta method, at each step, okay, we actually need to evaluate the f function 4 times, right? Because when we calculate the K1, when we calculate K1, we evaluate this function once, then K2 another time, and the 4th time. So computationally, it's much more expensive than the Euler method, right? However, the local error, like I mentioned before, the local error of the Runge-Kutta method actually is of the order delta t to the power of 5. We know that if delta t, usually delta t is small, okay, close to 0. And if delta t, for example, is 0.1, then delta t to the power of 5 is equal to what? Right? So for the same delta t, okay, but the local error of the Euler method actually is to the power of 2. So for the Euler method, this local error is actually 10 to the power of negative 2. So this one is actually much greater than, okay, 10 to the power of minus 5. That's why actually in practice, I would strongly recommend not to use Euler method, okay? And if you use the Euler method, although it's quick, but it's very likely you will get the wrong answer, okay? And in my opinion, okay, accuracy should be prioritized as the first, place. If you get an answer wrong, it doesn't matter how quickly you can get your answer, okay? You first need to get the answer right, okay? So now, since we talked about the step size, okay, delta t, okay, delta t is actually called the step size, which means the length of the interval we move from one point to the next one, okay? Like here, okay. This is delta t, this is delta t, and this is delta t, okay. So doesn't matter the Euler method or Runge-Kutta method we just described, okay? We always can use a fixed step size in the solution, which means I fixed it to 0.1, okay, for all, between all these points, okay, fix the interval as 0.1. However, if you look at this plot, okay, I just used the Euler method to solve this equation, and I use a fixed step size. Okay, this is called a fixed step size if this one is a constant. The problem is the approximation could be very wrong, okay, especially in the steep region, okay, right? But if you look at the tail region, looks okay. There's some small error, but it's okay, acceptable probably. But here, it's too far away, okay, from the true solution, and here is also bad. Here is also bad. So that's actually a common problem if we use a fixed step size, okay, when we solve the ODEs. So what do we want actually? What's the ideal step size we want? So we would like to have a strategy that can automatically reduce the step size so I can better approximate the steep region. However, I don't mind to have a longer or bigger step size in the flat region, right? That way I can get an accurate approximation to all the, all the parts of the trajectory, right? So that will be ideal thing, okay, to do. And also, one serious problem associated with fixed step size is that we actually will expect that if we reduce this step size, we will get more accurate results. Is that true? For example, if I use a big step size, then I should far away from the true trajectory, right? If this is my t plus delta t, okay. If the step size is too big, then I should far away from the true solution. Now, if I reduce the step size to here, okay, if my t plus delta t is here, then the approximation looks okay, right? So I can do same thing here. If I reduce my step size here, just use this small time interval, and to approximate the value, update the value here, looks still okay, right? So intuitively, you will see that if the step size is smaller, then you will get a better solution or more accurate solution. Unfortunately, okay, this is not always true. So here is actually an example. We just h here is the actually delta t, okay. Notation changed a little bit, sorry about that. But here h actually is the delta t, which means if I change the step size, okay, what will be my approximation error? Originally, we expected that this curve should be a monotonically decreased line if h gets smaller. Okay, I'm looking at it in this direction, okay. However, you see, you actually will jump back. So why is that? Actually, that's because the computer, okay, computer cannot store infinite digits of number, okay. After computer has a precision also. So after a certain digits, it will cut off the rest of the digits. That's called rounding error, okay. And once you cut that off, then you will get a small error, okay. So you need 2, okay. If you ask the computer to store number 2 in the memory, what indeed it stores is not 2, okay. Usually it stores is okay. So you will lose a small digits, okay. For example, like this, and this one usually doesn't matter, right? This one usually doesn't matter. However, here you also want your delta t becomes very small. Once these two actually become comparable, for example, your h also becomes this small. Then a small number divided another small number, you actually could get a large number, right? 10 to the negative 10 divided by 10 to the negative 20. What's the result? 10 to the power of 10. So you will get a very large number. So that's exactly what happened here, okay? So if you make your time interval too small, okay, this kind of rounding error will kick in, and you will get totally wrong answer. So that sounds like a big problem, right? So first, if I solve ODE, okay, I want to pick a reasonable delta t. Reasonable delta t, which means it will give me a solution that has acceptable error. Okay, but how? How to choose this delta t? Unfortunately, the answer is not depends. Okay, so there are some strategy we can actually control the automatically select the delta t, okay, step size. So if you're using ODE solver, okay, we call the numeric algorithm or functions that solve ODE solver, okay. If you use a solver in MATLAB or any other package you like, sometimes the solver will provide you a control parameter named step size. Okay, you can actually manually specify this step size, but I will not recommend do that. Okay, so here are two other actually control parameters. Actually, we usually use to automatically determine delta t. Okay, the first one is called absolute tolerance. The second one is called relative tolerance. The first one is more like a pre-specified number that a local error will be directly compared with. And the solvers in MATLAB or in a DDiscover, that's our own package, will give you a default value. Okay, so if you don't know what value to use, you can just start with the default value. Okay, same thing here. Relative tolerance, it will have a default value. And the product of this number with the current value of state variable will be compared to a local error. So that's actually the formula we're using to control the local error. So the relative error tolerance multiply the current value of x, now plus the absolute value, absolute tolerance. Okay, that's our total error we want to control. Okay, so by definition, if I decrease the absolute tolerance and the relative tolerance, will I get a better solution or worse solution? Error is smaller, which means the solution is better. Okay, so if I decrease these two numbers, I will expect to get a more accurate result, right? Now, so why people use this kind of tuning parameter or control parameter instead of just directly control the step size? Because the problems in practice, okay, have many different time scale. Okay, if you are modeling the long-term infection, you probably use the time of unit probably will be year. But if you're looking at the molecular interaction, the unit will be like a microsecond. So in that sense, you have to use a very different delta t, okay, for problems of different time scales. So to save that kind of trouble, you can actually just control these two numbers, okay? And for all the problems of different time scales. So that's one convenience, okay? So another thing we want to talk about is that here we have this error actually is specified by user, okay? We specify this relative tolerance, we specify this absolute tolerance, and we'll calculate the error. However, we need to compare this to something, right? Then we know whether this error is acceptable or not. Here we just calculate the error, okay? We didn't actually compare it with anything yet. So if we don't do the comparison, then we still have no idea, okay, whether we should increase the step size or decrease the step size. So that's why people also need to calculate when you use the algorithm, okay? The algorithm actually will do this for you, okay? You don't need to worry about this local error, okay? So how we actually get this local error? That's actually a chicken and egg problem, right? because we don't know the closed form solution of the ODE. That's why we use the numerical solution. Okay, and if we use numerical solution, and we have no way to actually to calculate the numerical error or approximation error, right, from the true trajectory, because we don't know that yet. If I shoot from this point to the next point, okay, if I have the exact solution or closed form solution, I will actually be able to tell what's the true solution here. When we use the numerical solution, we can only shoot from this point to the next one. The true solution we don't know yet, right? So that's why I'm saying it's a chicken and egg problem. Okay. However, there's some remedy for this. Okay. So the remedy to this problem is that we solve this problem twice. Okay. First time I solve it with a less accurate method. For example, RK4. Okay. Next time I solve it with no. Here it should be, yeah, because this one is more close to the true solution. So what people did actually is solve this step using a lower accuracy algorithm, RK4. Then I solve it again, use a higher accuracy algorithm, RK5. Then we take the difference between these two as a local error. Okay, that's what people do. It's not perfect, but that's how it works. Okay. So you solve it twice, actually. But the computing cost is not actually doubled. So there are some strategy actually to save some, computing costs. So actually, if you use this algorithm, you will evaluate the f function 5 times only. Okay. Not actually 8 times. Okay. It's not 8 times. It's actually 5 times in total. So once we approximate the local error, I can compare my user-specified tolerance with the local error. So what I will do is that if my user-specified tolerance is smaller than the local error, I can accept the current step size. If this error is greater than the local error, I will reduce my step size to half of the step size, and I calculate again. Okay, that's how the algorithm control. Okay, automatically control the step size. For example, if this step size is too big, okay, and the user specified tolerance is greater than the local error, what I can do is reduce the step size to half of the original step size. If this is still bad, I'm going to do it again. Okay. So in that way, you will find a step size that eventually such that this error will be less than local error. And then you accept that step size. So that's how the algorithm automatically determines the step size for you. Okay. So now here's an example. Actually, I'm solving the exact same problem, okay, as in this slide. Okay. In this slide, I used the solver with a fixed step size. And in this slide, I solved the exact same problem with a solver of automatically determined step size. So now you can tell in the steep region, the step size actually varied. Okay. This is not a fixed step size. This is a varied automatically varied step size. So now all the solution approximation actually falls on the exact solution. Okay, you don't get this problem anymore. Right? So now the approximation looks pretty well. Okay, overlapped. So that's why when you use the whatever package, I will recommend you to use accurate solver like Runge-Kutta method with automatic step size option. Okay, so this automatic step size actually increase the accuracy a lot, okay, in this region. So if you're interested in, or you have the MATLAB on your computer now, try this paragraph of code, okay? That's the code actually to solve the equation and the plot, okay, do the plotting. So now we have talked about the ODEs, okay? First order ODEs, okay? We call it first order ODEs because the order of the derivative is 1, okay? Which means we only take the derivative once, okay? But you can also get a higher order ODE, which means I can take the derivative of x respect to time twice. So you get the 2 dots, okay? Which equals to, that's also called ODE, okay? So what does this mean? We know x dot is equal to d dt x, right? Take the derivative of x with respect to t. If I put 2 dots there, actually what we do is take the derivative of x with respect to t once, and then take the whole thing, okay, with respect to t again. That's what it means, okay? You calculate the slope of the slope, okay? So that's the second order derivative. So if you want to plot it, actually, it's not that difficult, okay? So if this is my original curve, and then if I want to plot the derivative of this curve, then actually I'm plot the slope of this curve, right? I have a dot here, okay? So what will be the slope of the curve look like? This is a positive slope, right? Start from here, it's a positive slope, and gradually it becomes flat, the slope, because the tangent line of this at this point is this direction. The slope is 0. And then this slope becomes negative, right? So I will get a curve like sort of like this. Okay? So now, again, if I want to plot the slope of the slope, I start from here. Probably look like this way. Okay. Let's make it nicer. Okay, so what's the slope here? It's a negative slope, right? And it gradually becomes what? Positive? No. Negative, 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 still negative. But the magnitude becomes smaller, right? And then magnitude increases, but it's still negative, right? So if I plot the, oops, it is 0, I will start from here, that's negative, and the magnitude becomes smaller, which means it will closer to the 0, and then the magnitude will increase, then will go this way, right? So it always negative, but the magnitude, absolute value, okay, gets smaller and then getting bigger. So this will be slope of the slope, okay. So the so-called higher order ODE, okay, is just that kind of thing, okay. Slope of the slope plus the slope is equal to the x. So, we actually didn't bother to talk about this kind of models because all this kind of higher order ODEs can be converted to first order ODE, okay? That's why people don't bother to develop a specific method for the higher order ODEs, okay? So how we do that? The idea actually is simple. We just introduce a dummy variable, okay? Y here is called a dummy variable, okay? So now y is equal to the slope. Then I plug this dummy variable into the original equation. Then the double dot becomes y dot, right? Because y dot equals to x dot. So you put a dot on another dot. On top of another dot, you get the x dot. So this y dot actually is this one. Okay. So I do the same thing. Because x equals to x, y is equal to x dot, I will replace this one with y. Then eventually I get y dot equals to x minus y. Okay, now we go back to first order ODE again, right? That's what it is, okay. So now all the algorithms we talked before can be applied to this equation. So that sounds great, right? So you develop one set of things and deal with much more, okay, problems you expected originally. So, okay, that's good. So now let's relax a little bit, okay? So,
can you give us an example of where you would be doing a second order differential equation in a biological sense?
Yep. Actually, if you're looking at, for example, the diffusion problem, okay, let's just talk about the one-dimensional, okay. Diffusion problem, okay, the molecule, for example. I have a number of molecules, okay. I want to understand how they will diffuse along this direction, okay. So the concentration, let's use X denote the concentration. Yeah, let's use the X denote concentration. Then the first order derivative will be what? Will be the difference of concentration, the gradient, spatial gradient, right? And the force that push these molecules to move actually is proportional to this one. Okay. The gradient of the gradient, or the slope of the slope. So that's one example, okay. But if you're just doing, cellular or whatever dynamics, I don't think you have that many chance to actually run into this problem, okay. So now let's relax a little bit, because we have talked about lots of, mathematics and the notations, okay. Now let's just look at the graph, okay, instead of using the mathematical symbols. So there's another set of ODEs, okay. They call the stiff ODE, okay. Unfortunately, there's no rigorous definition for stiffness, okay. Although we call it a stiff ODE, okay. However, by looking at the trajectory, you can actually tell whether there's a high likelihood that the stiffness will occur. So usually, okay, the stiffness will occur if you see a trajectory that has a sharp turn, a sharp corner, okay, like this. Okay, so basically this curve has a comparatively flat region followed by a sharp turn or jump, okay, then a flat region and then followed by a sharp turn, okay. So what's the big issue about this kind of thing, this kind of model? The problem is that we have been talking about how to solve the ODE, okay, but if you have a stiff ODE, okay, the solvers I just mentioned, okay, will not work. Will not work means for this kind of simple system, actually this is produced by a two-equation system, okay, just two equations. You probably need to spend like 8 hours to just solve it once if you use the two solvers I mentioned before. It's not acceptable, okay, for a small system like that. You want to spend 8 hours to solve it. So the problem is, remember, when we talk about the step size, we said the solver will automatically determine the step size, okay, such that in a flat region, I will use a bigger step size. In a smaller in this steep region, I'm gonna use a smaller step size, right? However, because the regular solver, okay, when they try to do this, okay, around this corner, this delta t will becomes extremely small, okay, so such that you have to solve this evaluate the f function, okay, millions of times, and eventually, actually, usually they're gonna just fail, okay, will be just stuck there, because you keep reducing the delta t, reducing the delta t, and then you have to keep evaluating this function, so it will stuck there, it will not move, because the local error, okay, cannot satisfy the criterion we just mentioned, okay. So even the solver keep reduce delta t, okay, this one still cannot be satisfied. That's why the solver cannot move from one point to the next point. So that's why actually people have to use the so-called steep solver, okay. We have a category of solvers that are designed to deal with this kind of steep problem, okay. It's called a steep solver. Mathematically, okay, how the solver deal with this kind of problem is by calculate the eigenvalue of the Jacobi matrix, but who cares about Jacobi matrix for now, okay? So we just know that it's gonna work if you use a specific solver, okay, for this kind of problem. So if you use MATLAB ODE 23S, that would be the one you want to try. Or you can use our package, okay, we have a Rosenbrock solver in DDiscover. And if you're a MATLAB user, you just need two lines of code, okay, to solve a stiff equation and do this plot, okay. Yeah, there are many other alternatives. If you're familiar with the grammar of MATLAB, there's a free alternative called Octave, okay. It uses the MATLAB language, but this one is free. And many of our statisticians actually on Wednesday, they're going to talk about lots of data analysis thing. They use R. R also can solve. It's free. Yeah, R can also solve it. And there are many, tons of packages actually can.
We use MATLAB, but it's a license.
This one, then if you are familiar with MATLAB, then this one you can try, Octave. This one is free, okay.
How about the next one?
You mean the stiff solver? Oh yeah, it has all the usual solver you need, okay. So you don't need to worry about actually the completeness. Okay. Question?
The main problem that you have several y values for particular x values. Is that why it takes so long to solve it?
No. Remember, for now, okay, we only talk. I actually used one-dimensional problem to illustrate the idea. Okay, I just talked about x dot equals to ft x theta. Okay. However, the model we used in practice usually is not one-dimensional. Okay. Usually we have x1 equals to f1 t x1 x2 x3 theta. For example, it's a three-dimensional system. I have x2 x3 f2 f3. Okay. Usually you will have this kind of system, multi-dimensional, okay, system. So it doesn't mean, okay, if I will spend more time to solve it because I have more variable, okay. The problem is that if just one of the variable has this sharp turning corner, okay, it will cause a problem, okay. Even if, for example, if the plot of this one looks like this, but this plot may look like this, okay. It can be flat, sort of. So different variables, they can have a very different trajectory. And you can put them together, solve them, okay. Is that clear? Or okay. So Now, let's talk about another category of the ODEs. Okay, it's actually a variation of ODE. It's called a delayed ODE. So we have been talking about ODEs, okay, general ODEs. So the problem is sometimes you need to consider the delay effect. For example, we know that dendritic cells stimulate the CD8 T cells, okay, for their affinity maturation, right? The problem is we actually observed the dendritic cells in the lymph node or spleen probably around 1.5 days after the infection. However, the appearance of CD8 virus-specific CD8 T cells is usually after day 5. Right now, I'm talking about influenza virus. For different viruses, the number could be different. Okay, so from the stimulation to the affinity maturation, there's actually a 3 to 4 days delay. Okay, so if you want to account for that kind of delay in your model, that's the timing you should use delayed ODE called DDE. Okay, so the difference between the ODE and the DDE is that right now you have a delay term. Okay, tau here is time delay. Okay, so the problem is that once you want to use the DDE, you have to specify the so-called history function. Remember, if I don't have this term, then the left-hand side is x dot t, that's the value or derivative at time t, and the right-hand side, we also have the value at time t, right? But once you introduce the delay, now the value of x at time t also depends on the value of x at history, right? Or the historical value. You have to plug in a historical value to calculate the current value. So that's why you need to also specify the so-called history function. Okay, if you don't have this one, then you will be totally wrong. Okay, I have to say that. So if you don't specify the history function before the initial time point, okay, then you will get this wrong. That's one thing we need to pay attention. Another thing is that a new problem associated with DDE is that the discontinuity in the history function will propagate into the higher order derivatives of x. So I bet that you don't understand what I'm talking about. So that's fine, because this one, okay, when you specify this function, okay, this function can be a continuous curve, okay, up to t0, right? But sometimes people also use a discontinuous curve trajectory. For example, I may have a history function like this. So I have a jump here, and here is my t0. So you have a jump here. Can everybody see it? Or I just happen to draw behind the computer. But anyway, once you have this jump, okay, this jump will propagate into the derivative. So actually, just look at the equation, okay? If I have a jump in edge, so the edge will goes to this part, right? And then the jump will go to here, because your equation says the derivative depends on this jump. That's what I mean. Okay. So why does this jump matter? Because it will change your solution. So either you use a continuous, okay, either you use a continuous history function, but if you do have a jump in your history function, then you have to use a particular solver, okay, for this kind of problem.
So in this case, the function is not variable in all the time domain. I mean, there is a discontinuity.
If there is a discontinuity in the history function, you still solve this one forward. Okay. So I'm not saying that it becomes some other type of problem. It's still a forward problem. The problem is you need to pay attention to that, because if you use the solvers I mentioned before, then we again get a wrong answer. The point is that use the particular solver, okay, for this type of particular problem, okay, then you get away from troubles, okay. Otherwise, you again probably will get a wrong trajectory. So for now, okay, you probably is a little bit nervous, okay. So modeling is not as easy as right as what we talked about this morning, right? So there are many tricks, okay, and pitfalls, okay. You have to actually to know, okay, before you use the models, okay. If you don't know, okay, the issues associated with each type of different problems, then you get yourself a lot of trouble, okay. That's not actually rare, because when I was going to some other conferences, okay, I saw actually a simulation work did by some, labs, and they just made some assumptions that she eventually denied to, decide not to, argue with me. So because she's looking at the fish population, and she made an assumption that there is an infinite number of fish at the boundary. I said, how could that be possible? Okay, so again, okay, that's a particular issue, okay, associated with a particular problem, but you have to know that, okay, beforehand. But anyway, the last variation of ODEs is actually the so-called differential algebra equation, okay, DAE. So the concept of DAE actually is simple. It's just the ODE plus some equality constraints, okay? So these are constraints, okay? Although I use the same edge, okay, at many different places, okay, but here edge means the constraints. For example, if I have x dot equals to something, y dot equals to now I want to solve this on the circle, okay? If I'm only interested in this on a circle, I put a constraint like this, okay? This is a circle, okay? If you move it, it gives you, right, equals to 0. And if you plot x, y, that will be this circle with a radius of 1. Okay. So if I want to just solve this ODE on this circle, that's what we do. So sometimes you have a geometric constraint or whatever constraint, okay. That's how you handle this. Again, you have to use a particular solver, okay, for this problem. For example, in my lab, you use the ODE 15S or ODE 23T, okay. That's the two solvers you can use to solve DAE. Okay, had enough of ODE. Yeah, I'm a little bit sick about it. So let's, last thing. Here actually are 3 books you can read if you're really interested in ODEs and DDEs, whatever, DAEs, okay. So this is volume 1, volume 2, okay. The first one is for the non-stiff problem. The second one is for the stiff and the DAE problem, okay. This one is about DDE, okay. Although I have to say this book is not perfect, okay, but that's probably the only book available right now, okay. So let's watch some video, okay. So there are legends on the screen, so you will know what they're doing. Okay, so this simulation is about the blood cell flow. Okay, you actually solve some equations to get this simulation. Is that fun? So now we try different parameters, okay? And we compared with what we know about the cell flow. and to tell which parameter is more realistic. Okay. So sometimes, you know, if you don't have music, the video just looks silly. Actually, I think the original video actually comes with pretty cool music, but I sort of removed it. And here now we are looking at the clustering phenomenon, okay, in the cell flow. And now we're actually looking at the stress, okay, on the cell membrane. So the red means there is a higher stress, the red color. Now this is a shear stress. And you see a bunch of, deformed cell shape. Okay, cell shapes here. They're all the same type of blood cells, but these cells deformed due to the shear stress. Okay, do you want to stop here, or you want to keep watching it, or okay, question?
Yeah, so like, what kind of literature findings or data did you?
You don't need data for this. You just create a model and solve it in computer and generate visualization results. You get a movie. You don't need data. Oh, you do need some data. For example, the physical properties of the membrane or the fluid. That's some value you can take from literature. But you don't actually need to measure anything for now. Okay.
Do you know if in this work the result that this Boltzmann matched with the prediction by Navier-Stokes?
Mm-hmm. What you just mentioned, what you just mentioned actually is very computationally expensive. Okay, but the idea is right. You couple the movement of cells with the fluid dynamics, okay? But you will not bother to use the Navier-Stokes equation because that's too much, trouble. Okay, so this one actually, the way I just showed you, unfortunately, is not solved by ODE. Okay, ODE cannot do this, so that's why we talk about PDE. Okay. So when we use PDEs, okay, as I mentioned before, we can actually take the spatial difference into consideration, right? And that's what it can do, okay? This PDE, okay. So this is actually I wrote a simple program to use PDE to simulate the gas diffusion, okay? In my lab, actually, you start from a spot, and then you look at how long it will take for this gas to diffuse into the neighborhood. Okay, so at different time points you can plot this diffusion. Okay, and eventually this gas covered the whole region you're interested in. So this is also done by PDE. Okay, now you can tell because there is a spatial difference. Okay, that's why I use PDE. Okay, because originally the concentration of the gas is very different from the concentration at any other places, right? So eventually everywhere becomes the same. Okay. So what are PDEs? Okay. Since we have watched a fancy video, okay, now probably we want to know a little bit about PDE. So PDE itself is similar to ODE, but with additional derivatives. So in ODE we talk about now I switched the symbol again because I have to use X here, okay, for another purpose. So we used to use X to denote the state variable, but now I use X, Y, Z to denote the spatial coordinates. Okay, that's a 3. Okay, spatial coordinates x, y, z here, and the t again is our time variable. So our independent variable in this model will be like how many independent variable? 4. We have t, x, y, z. Okay. Right now we have 4 independent variables. In ODE we only have 1 independent variable. That's t. Okay. So now we have the spatial coordinates in the system, and also we take the derivative of the state variable. State variable right now is u. Okay. We take the derivative of u respect to t, x, and z. Okay. Now you probably also noticed that the notation for derivative changed. Okay. So this morning or 5 minutes ago, okay, we're talking about derivative, and the notation is small d, small d. Okay. Now here in this notation it changed to u. Okay, notation changed. So this is still derivative, but it's called partial derivative. Okay. Partial, okay. Derivative. So what does partial derivative means? If I have a function of time and x and y, okay. If let's say u is a function of time and also spatial coordinates x and y. So the partial derivative of u with respect to t is that so I fixed x and y. See, I use the same x and y in these two terms. So x and y keeps the same. Okay, I only change the time. Okay, and if I change the time, then I calculate the difference divided by the time interval. That's called partial derivative, which means I fixed other variables and only look at the change in one variable. That's why it's called partial derivative. Okay, that's the definition. So now let's look at some difference between ODE and the PDEs. The first one is that we have talked about this for quite a few times. Is that spatial homogeneity. Okay, ODE assume that there's a spatial homogeneity. However, PDE does not. So it can actually describe the changes over both time and space. ODE has only one independent variable, t. Okay, PDE actually can have 2 to 4 independent variable. Depends on how many spatial dimension you want to take into your model. Okay, you can consider like one-dimensional PDE. Okay, that's also fine. One-dimensional, which means one-dimensional in the space. Okay. So higher order ODEs can be reduced into first order ODEs, but the PDEs cannot. Okay, unfortunately. Okay, remember we can reduce this equation. Okay, into a first order ODE, right? By introducing a dummy variable. However, for PDE you cannot do that. Okay, there's no this kind of simple way to let you to reduce simplify the problem. And another bad thing about PDE is that the existence of the solution, okay, is difficult to tell. And so far, only a limited number of PDEs can be solved. Okay, even using numerical method. So that's bad news. But fortunately, okay, for many of the PDEs, okay, we will use actually in research. We do have tools and algorithms to deal with that. So here's some classical PDEs I want to actually go through. Okay, what you need to know is just the name. Okay, what's a form? Okay, you don't need to bother to understand any of the properties or whatever. Okay, so when people talk about the Laplacian equation, it's just you add the partial derivative, okay, second order partial derivative together, and the left hand side then equals to 0. That's called the Laplacian equation. Okay. So this notation here means I take the second order derivative with respect to x, which means I take a derivative once and then again, okay, to the same variable, with respect to the same variable. Okay, so that's what it means. And this one is a diffusion equation. That's actually the equation I just used to generate this plot. Okay, it's a two-dimensional diffusion equation. Okay, you can solve. And here is the wave equation. So I suggest by name, you can use this to describe the wave, water wave, or whatever, earthquake wave. Okay, doesn't matter what kind of wave. Okay, actually people use this equation to evaluate building safety. Okay, against the earthquake. So once you have an earthquake, actually you will get waves propagate in the soil. Okay. And then this vibration will propagate to this building, and this building will start to shake. And you can actually use this kind of equation, okay, to predict, okay, whether this building will fall apart or survive. What? Oh. This notation, okay. So that's why people hate mathematician, okay. This one means first order derivative. Okay, and if I put a square there, then it becomes a second order. That's which is what we saw on the slide. Okay. Okay. So, since you asked this question, I have to mention. Okay. This is not a summation. Okay. This is a vector. You get a vector of 3 elements. Okay. If it's a gradient, this is called a gradient. Okay. This is not a summation. Okay. This one is a summation. Okay. So there's a difference here, but if you think it's not important, okay. But anyway, they're different. Okay. So, but it doesn't matter to actually what am I trying to deliver here. Okay. I just want to show you some classical PDEs, okay, used in engineering or whatever. And the next one is just mentioned by I don't know what's your name. But anyway, Navier-Stokes equations. One equations you describe almost all the fluid dynamics. Okay, use this one equation. Okay, all fluid dynamics can be described using this one equation. Okay, that sounds perfect, right? But unfortunately, okay. For specific problem, okay, you can actually earn yourself a PhD degree, okay, by solving one specific Navier-Stokes equations, okay. So by play with the boundary conditions or whatever, okay. So that's how I actually get my PhD degree. Anyway, so okay, for people who are interested in molecular dynamics, okay. The Schrödinger equation, okay, that's what you should know. Although you don't need to care about the technical details, but that's a name, okay. Quantum mechanics, okay. It's also a PDE. So PDEs, for simplicity, we can also actually classify, okay, the PDEs, okay, into either linear or nonlinear PDEs, okay. And the linearity actually is respect to u, okay, the state variable or dependent variable, okay. So this one is a linear PDE. This one is not, because u right now is in the denominator, okay. So also, if you look at PDE, you probably also will hear people talk about the elliptic, parabolic, hyperbolic. Make it simple, okay. That's just for some historical reason, okay. People would classify the PDE in this way, but when you solve a PDE, okay, you probably can actually don't need to pay attention to this, okay. Just some terminology, okay. So if you have a second order PDE in this way, you just look at the coefficients, okay. If this relationship holds, inequality holds, you call it elliptic, okay, whatever. So that's just some terminology. So now I'm gonna talk about how to solve them, okay. We have talked about the PDEs, we watched the video, okay. Now we want to know actually how to solve them. So to solve the PDEs, the first classical method is called the finite difference, okay. Actually, we have talked about the finite difference method already. This is finite difference method, okay. The partial derivative is approximated by the difference after the interval, divided by the interval. And that's called finite difference. Okay. So there's nothing magic, okay, about this method. So by doing this, okay, the advantage is that you can convert the PDEs, okay, into a linear system. That sounds good, right? PDE itself looks pretty complicated, okay, as we show here, right? But now if I can convert this one into a system like this, this is a matrix. Is there anyone who doesn't know what is a matrix? I don't think so, right? Or there does? Okay, I got an answer. So, what is called vector is actually a bunch of number, okay, you put them in a column. That's called vector, okay. That's a vector. So you put some numbers in a column. That's called a vector, okay. And when we say matrix, it actually is multiple columns of numbers, okay. So there's nothing, mysterious here. This is a matrix, okay. A matrix that has 9 elements. This is a vector that has 5 elements, okay, or 5 because we have 5 numbers, okay. And this one has 9 elements, or we call it 3 by 3, okay, because we put the numbers in this way: 3 rows, 3 columns, okay. So that's a matrix. So now what I can do using FD method is that I can convert a PDE into this kind of equation. So a matrix multiply an unknown vector equals to another vector. What I need to solve is x. For example, 1, 2, 3, 0, 1, 2, 0, 0, 1. That's my A matrix. And what I want to solve is x1, x2, x3. Or let's use U, okay, U3. And this one is equal to, for example, 4, 5, 6. Okay. This is what I call the linear system. Okay, this is unknown. And you probably ask, okay, what the hell is this? Okay, this one actually is equivalent to what? Mu1 plus 2 mu2 plus 3 mu3, which equals to 4. See, row by column equals to this element. Okay, that's a product of matrix and vector. Row by column. Okay, you put 1 with mu1, 2 with mu2, 3 with mu3, and add them together, and you get 4. Similarly, for the second row, I can put 0 with mu1, you get 0. 1 with mu2, you get mu2, and 2 with mu3, and equals to 5. So I can also do the same thing, right? For the last row, 0, 0, u3 equals to 6. So this system is equivalent to this system. Okay. It's just a notation, okay, for simplicity, okay, of notation. People write it in this way, but indeed, okay, these are 3 equations, and you know how to solve it, right? Because this one is pretty simple. U3 is equal to 6. Plug this back to here. You can solve it for U2, right? Then you plug U2 back here, U3 back here. You can solve U1. Okay. So that's a linear system, and how to solve a linear system. Okay. So a key step in a finite difference method is that we actually divide the problem domain into grids. Okay. That's how we can actually generate this linear system. So for example, okay, here, if our problem domain is a square, okay, then if I want to solve it, I actually divide this problem domain into smaller, much smaller squares. Then what we want to know is u, right? Then we use the value of u at each grid node, okay, to approximate the derivative. Remember? Oh, I already erased it. But for example, dx, right? We can actually use these two nodes to calculate the derivative here, right? The change in the value divided by the interval, you get the derivative here, right? So that's actually the idea, okay? Totally the idea. You can do the same thing in the time domain, okay? So if we look at an example, remember we have a Laplacian equation. That's a second order partial derivative, and we just use this approximation, okay? Calculate the slope of the slope, okay? It's just the approximation to the slope of the slope. So you know how to do it, right? We have talked about it, okay, before. So you just plug in this approximation into the original equation. That's all. Okay. So for example, if you let delta x equals to delta y, you can get an equation like this at each grid node. Okay. That's what you actually come. That's actually come from here. Okay. From here to here. If you don't mind to do some, simple mathematics, there's nothing, difficult here. You just let these two be equal, and then these two can be canceled out, right? Then you just rearrange the denominators, and you get this one. Okay. So also that here the u, all of the u are unknown. Okay, we don't know what's u yet. However, at each node we can get one equation. In total, I will get I multiply j equations, which means hundreds of equations or thousands of equations, and that actually can be written in this form. Okay, these hundreds of equations eventually will be arranged into this form. And then you solve for the u, okay? So that's a basic idea. However, I personally just don't like the finite difference method because there's something called the finite element method, okay, which is way more flexible and stable than the FD method, okay? And again, the finite element method actually approximate the problem domain, okay, using something they called elements. That's why they called finite element, okay? For example, here's the model that actually model the stress, okay, in the human body. You see a color here, okay? That's a distribution of the stress. And now I use actually the pyramid, okay, element to divide the whole problem domain into smaller elements, okay, thousands of elements, okay? So, of course, for different problems, you can use different elements, okay, to divide the whole problem domain. And then what I do is not actually like what I did in the finite difference method. Instead of approximate the derivative, okay, I actually do an integration, okay? I do an integration and then use some mathematical, techniques. You can actually reduce the order of the derivative, okay, by introducing a weight function. And this kind of trick, okay, is not important for now, okay, because that's not what we want to learn, okay, for now. But eventually, I also get this kind of linear system, like the finite difference method, okay. There are two different methods, because one method is FD method directly approximate the differentiation, okay, operator. And this one, finite element method, actually do integration, okay. And that's also the reason I talk about integration at the very beginning of this talk, okay. So, fortunately, okay, like ODEs, okay, you don't need to struggle with the implementation of FD method or finite element method. There are many available packages, okay, and they can actually deal with very complicated problems. Probably some of you know the FE Bio. It's a package designed to simulate biotissues, okay, or blood flows. You can use this package, and this one, and this one, and this one. They're all free, okay. These 4 packages are all free, okay, and I think they're all written in C or C++, okay. And here are some commercial packages, okay. If you have the grant money or whatever money, okay, to pay for the license, okay. Although I have to remind you, it's pretty expensive, okay. The package I will recommend actually is something called Comso, okay. Comso is an amazing package, okay. You can use to model many, dynamic problems, okay. So now let's move away from differential equations, okay. Is that too fast? Or I had thought I should have a 10 minutes break, but anyway, let's try 2 hours, so optimization, okay. So what do we mean by optimization? Optimization, because we want to find out the optimal balance between something, optimal cost, which means minimal cost, right? Or we want to maximize the productivity. Okay, so optimization means minimization or maximization. Okay, that's just optimization. So But to minimize or maximize, you have to have something to minimize and or maximize, right? So what do you want to minimize or maximize? That kind of thing is called objective function, okay? We have a name for that. Objective function. So what we want to do to this function is to either minimize or maximize this function by changing or search and best set of parameter value. That's it. For example, we want to know what's the best parameter or best material that I can use to build a house, okay, given the total amount of money I have. For example, what's the best house I can build given 100K? Okay, then you have parameters to choose, right? For example, what's the percentage of steels you want to use? What's the percentage of wood you want to use as building blocks, right? So this percentage actually becomes your parameter. Okay, for our problem, okay, for modelers, okay, what we really care about is so-called model fitting, okay. We don't care about other things, okay. We care about model fitting, which means how can I infer parameter values from data given the model structure, okay. What's the best parameter values that I can best have my model prediction be closest to my data, okay, if I interpret the optimization problem in this way, okay. So here is a typical problem of optimization. It's called least squares. How many of you have heard about least squares before? Okay, 50% approximately. So what's least squares? Least squares, which I use a simple example to explain, okay? If I have a bunch of data points, that's black dots, okay? And now my goal is to find out a straight line that is closest to all the data points, okay? Not to just one single data point, okay? I want a straight line that is close to all the points, okay? Which means this line fit my data the best. Now, how many possible or candidate straight line I can have? Infinite number, right? I can draw a straight line here, right? I can draw a straight line here, 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 okay? So I shifted it, okay, in the vertical direction. I can also rotate the straight line, right? Change the angle, change the slope. So I can have actually infinite number of straight lines that can describe the data. However, there's only one line that is closest to all data points. And what we're trying to do is find out that straight line. Okay, so what we do is actually that we know that we can use A plus BT to actually model a straight line, right? That should be that would be the first agreement we should have, right? If you're saying we have to use a different model, okay, to model straight line, then we were in a different universe, okay. So, but anyway, use A and BT, okay, we can describe a straight line. So what we want to find out is what's the value of A and what's the value of B. That I can actually draw a straight line that is closest to all data points. So now I have to define an objective function, right, to minimize or maximize. So here, since I'm talking about closest, so I want to minimize some function, right? So minimize what? Minimize the distance from the data points to the straight line. Okay, so what's the distance from the data point to a straight line? So here to here, that's distance, right? So here to here, that's distance. So all this, red dashed line, they're actually distance. So now if in mathematics, okay, the distance actually is, this is a straight line, subtract the data. Okay, yi here is our data. I use a notation here, yi. So this is a value on the line, right? This is a value on the line, a plus b ti. Okay. This is a value on the line. This is the data. So I subtract these two. Subtract one from another. Then I get a distance, right? And then I put a square there. So this distance can be positive, can be negative. But after I put a square there, the square will be always positive, right? So now I'm okay to minimize it. Minimize this function, and then you will get the best a and b you want. So that's called the least square, okay? Square. Square part is here, least part is here. It's called the least square, okay? So is that clear? Question? Good. No question is good. So now let's talk about, okay, how to actually find out the best a and b. So one brute force method will be, what will be the brute force method? I just try many different a and b, right? And I compare them, and I find out the minimum one, right? So for example, I can generate, let a computer generate a list of a and b. I can let a, b, and here's my f, a, b. I can have a 1, 2, 1.12, 1.22, 2, 2, right? I can have 1, 1.1, 1, 1.2, 1.3. I can plug in many different pairs of values into this function. Okay.
In these squares, are you determining the distance from the dot to the line? Is it the closest distance from the dot to the line in terms of like perpendicularly, or you're just doing it for
Yeah, it has to be, for this case, it has to be not perpendicularly. It's just in a vertical direction. Okay. It's in a vertical direction. It's not perpendicular. Perpendicular will be in this direction. Okay. Here now, we only calculate the distance in the y-axis. Okay. So, because we assume the distance in the x-axis actually is t here. We fully specify the t, so we don't want to bother to include this one into the distance. Okay. So you only calculate the vertical distance. So now let's talk about how to find out the a and b. Okay. I can generate this table. Okay. And plug this number, the parameter values, into the function. And probably this one I get 5, this one I get 10, this one I get 1, this one I get 30, whatever. Now I compare them. Because this one gives me the smallest value, okay, I think, okay, my parameter should be 1.2 and 2. Okay, let's minimize this function, right? However, this method is stupid, right? Because there are infinite combinations you have to try to figure out the answer. Okay, that's why people derive the so-called gradient descent method. This kind of a so the idea is if I move from one starting point, okay, because here the slope is negative, right? The slope here is negative. So I just move along the slope direction. So I decrease the value a little bit, right? Because right now I want to minimize my object function. So I will move along a direction that leads to a smaller object function value. So now I move along this direction. That makes sense, right? Now from here I get to here, and my object function value becomes smaller. Again, I start from here and move a little. Does that look like the ODE solver? A little bit, right? So But now the independent variable is theta, okay, instead of t, okay. So actually, that's exactly the same idea, okay. We solve ODE, we start from one to the next by calculate the slope, right? After we calculate the slope, we move along the direction of the slope and get the next point. Here's the same thing. I move in this direction because the slope is negative. I do not move in this direction because if I move in this direction, that will increase my object function value. So you know this direction will lead to a smaller object function value. That's why you move in this direction. And I do the same thing here, Eventually I got to the nadir. Okay, that will be the point I want. Okay, so my best parameter value actually corresponds to the nadir, okay, in the object function curve. Does that make sense? That's the basic idea, okay. Mm-hmm. You want to draw a horizontal line, or? Well, that's true. That's very true, actually. So if you have not just this one, okay, an arbitrary curve, okay, the minimum and the maximum always occur at places like here, 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 here. And one common property of these points is that the derivative here, the slope at these places are always 0. Because if you draw the tangent line, okay, you actually get this. But the problem is, if I have multiple this kind of points, which one you want to choose? Right? Here I just draw a simple case. This one has only one, place that has a 0 slope. But this one, if I have multiple, 0 slopes, you solve this equation, but you get a multiple solution. You have to choose one, right? So this will be the so-called gradient method. Okay, you start from one point, then move move in a favorable direction, and then you search the minimum. The key problem is that so what's the problem you can tell, okay, from this plot? The first problem is, where should I start? Right? How about I start here? Then I just move once, I get a solution. But do we know where to start beforehand? No, we don't. Okay, usually, okay, for the problem we don't know where to start. We have to guess. Okay, that's the biggest problem for this kind of method. If my guess is wrong or too far away from the true solution, you get into trouble. For example, here, okay, this is actually a real object function, okay. If I start from here, let's say here I want to maximize, okay, maximize my object function. If I start from here, then follow the gradient direction, I probably will just stop here, right? I will not move away from this point anymore. Because I think that's already my answer. The gradient method will take that one as the answer. Okay, it will not search for a better solution. Okay, once it reaches a local minima or maxima. So that's the same problem here. If the true solution is here, but if I just start from here, I go along in this direction, and then I get to this solution, and then the gradient method will stop here. It will not move anymore. Okay, once it finds a local minima. So gradient method is a local method. Okay, if your guess is far away from the true solution, you will get a wrong answer.
How did you find a global minimum?
Thank you for that question, because this is a motivation, okay, for the global method, okay. So we want to find the global solution, okay, instead of a local solution. So this is another example, okay. You can actually check the help file in MATLAB, okay. It has an object function that has this many bumps, and you know, and the two solution actually is here, okay. If you start from here, you never actually, if you use the gradient method, you will never get from here to here, okay. So that's why people actually developed the so-called global method, global optimization method. One typical algorithm is called the genetic algorithm. I think all of you should have heard about it, okay, before. Genetic algorithm. So the genetic algorithm actually mimic the evolution of genes, okay. That's how it works. So it has 4 steps. The first step is the inheritance, which means the next generation or the children will be generated from the parents, okay. That's called the inheritance. And the second step is called mutation, which means the genes of the children will be mutated. So they will be different from the genes of the parents, or they are not exactly the same, right? The third one is crossover, which means after mutation, by the selection force, you may keep some of the mutation, but you may just keep the genes from your parents, okay? So you have a crossover. And the last one is selection. So let's skip the technical details, okay? And then instead, I want to actually draw a plot to explain why this genetic algorithm can find the global solution, okay? So I still have a object function like this, okay? Now, instead of start from one particular point, I will randomly generate many points spread out, okay? For example, I put points everywhere, okay? For example, if I allow 100 search agents, okay, let's call this point search agents because they are searching the global solution, okay. So let's call this point search agent. So I let this search agents, okay, spread out, okay, in the whole parameter space. Okay, you can do this easily by generate uniform distributed random numbers. Okay, you can do the first step. Then you will say, okay, now I have many starting points. Okay, then one of them will actually move along the direction and get to the global solution. Okay, that's a good. That's actually a good wish. Okay, the problem is if you have a function like this, okay, most of your search agents will stacked by the local minima. Okay, you still will not have a global solution. So the solution actually is we need certain strategies, okay, to explore the whole parameter space. Okay, instead of randomly, okay, let them search. We need some strategy. Okay, so strategy is that after I generate the initial search agents, okay, I generate the next generation. Okay. So I generate next generation of agents. They are children of the previous generation. And these search agents actually will update themselves from the parents, not only by mutation, okay? You see, here's mutation, but also selection and crossover and selection. So mutation here is simple. I just randomly select 3 search agents in the previous generation and add them together, okay? Basically, this is a difference between 2, amplify the difference, add them together, you get a mutation. But a mutation could be good, could be bad. And then you do the crossover. Crossover means you mix the genes of the mutated genes and the parent's gene, okay? Mix them, okay? Next step is that if the children are better than the parents, then we replace the parents with the children. That's selection. So in that way, I will generate my search agent eventually will get better or get closer and closer to the solution here, here, here. So basically what I'm saying is that all the local minima or maxima, there will be, the search agent will get crowded there. Okay, then you will have a best one. Okay, so in that way, it actually search the whole parameter space, and then one of them is the best. So that's how this kind of genetic algorithm get the, global solution. So instead of a generic algorithm, people also develop many other things. Okay, interesting things. You can mimic the behavior of ants. That's why you get the so-called ant cloning algorithm. You can mimic the behavior of bees. That's why you get the artificial bee cloning algorithm. And you can also mimic the behavior of birds. That's how people actually develop the so-called particle swarm. Okay, so we actually were inspired by the nature. Okay, a lot. So, but in nature, okay, these algorithms called evolutionary algorithms. Okay, the concept, okay, is actually similar to what we just described. Okay, you use the parents, okay, generate the children, and follow some strategy and do a selection. Okay, so there are similar things. They can all be used to find out the global solution. So now I will actually want to show you some movie. So how the global algorithm work. Okay. You see, the surface actually is the object function surface. Okay, it has many bumps, and what we really want actually is this one. Okay. And I have many search agents, and they're exploring the whole parameter space, and eventually it goes to that solution. Okay, now it will converge. Okay. So that's how it works. So the important thing is the idea, right? It doesn't matter the technical details. Okay. So I think I have 2 minutes, but probably I will not take advantage of it. 15 minutes? You want me to talk 2 hours and 15 minutes? Okay, that's fine. That's not humane, okay? But anyway. So let's talk about the different types of algorithm, okay? We talk about the gradient-based method. We talk about the global method, right? Actually, there are more methods, okay? This category is called a direct search, okay? Here I just put a bunch of names, okay, here. You don't need to care about the details, but once you met them, you know what they are, okay? That's enough. So for the gradient method, we just talked about, okay? I will recommend the sequential quadratic programming. That's the algorithm I always use, okay? But I actually do not directly use this one, okay? I combine this method with some other method, okay? That's how you get reliable results. I'm gonna explain that in like 2 minutes. So the second category of optimization algorithm is called a direct search. They're slow, they're local method, so don't bother to use them. That's all. And the third one is called global method. I just talked about, right? The differential evolution method, a genetic algorithm. So there are many variations, okay? But you just remember the video, okay? That's all, okay? The video tells you how they search the parameter space and get the global solution. Then we're okay. So this final set of algorithm is called hybrid method. That's actually what I used in research. Basically, you know that grading method is not reliable because you need to pick a starting point, and which you have no way to know how to pick that. Okay, you have to guess, totally by guess in many situations. Okay, also the grading method will just converge to a local minima. Okay, so that's another thing you don't like. You don't have a global solution. Now, if I use global method, I can have a global solution, but one thing I didn't mention is that this kind of method are extremely slow. Okay, the computing cost is very high, so you don't want to like wait 1 week to get an answer. So even that's why people actually develop the hybrid method, or called mimetic method. Okay. Idea is that let's just combine, okay, the grading method and the global method. So you can get a global solution with much improved computing efficiency. Okay. But this kind of method is still slow, but much faster than the pure global method. Okay. And also, since you introduced the grading method into this kind of approach, then you are guaranteed to converge to the local minima, right? And also, since we have some strategy to ensure the search for global solution, then you get both. Okay, that's one good thing about this one. And tomorrow we're going to talk about DDiscover. We actually have all the 4 types of algorithm implement, and you can try different method to see which one works better. Okay. So that's actually the advantage and the disadvantage I just talked about. Okay, basically just the global solution versus the local solution, and also the computing efficiency problem. Okay. So now I have 10 minutes, so let's start with the stochastic simulation. Okay. Let's watch a video again. Okay. This time I got music. What you are watching right now, the red blocks, they are intruders, okay? And the yellow dots, they are bees, okay? And this green bar is the total amount of food available to bees. And the red bars are total amount of food available to the intruders. So the intruders are trying to steal foods from the hive. Okay, and once they get closer to the hive, they get some guards. Okay, fighting against them. Okay, you see the purple. There are some purple dots here. That's actually the guard. So the number of bees actually depends on the total amount of food. Okay, similarly the total amount of intruders depends on the food, but also their, migrations or something. So sometimes they will just move away from the frame. Means they find another place to start over. Okay. And these green squares, they are actually flowers. Okay, where the bees can get flower powder. Okay. Okay, so I guess that's a highlight of my talk. Okay. But anyway, to generate that video is actually extremely simple. Okay, I have to tell you. Okay, visualization is complicated, but generate that data. Okay, for visualization actually is very simple. You just draw random numbers. Okay, keep drawing random numbers. Okay. That's actually the basic idea of stochastic simulation. Okay, Stochastic simulation is just drawing random numbers, okay? That's all. So, but since I still have a few minutes, so I will not stop here. So I have to talk about some details of how to draw in random numbers, okay? So, but before that, let's look at this plot. So that's actually the case that randomness will become very important. This actually comes from a Nature review paper that looks at single cell data. So that's the same type of cell, 7 cells, or the same type, and they're undergoing the same biological process. However, if you measure the protein, okay, one certain protein concentration within each cell, the data pattern looks totally different. So since there are same type of cells that are undergoing the same biological process, we expect that we can use the same model to describe the data, right? However, the data pattern looks totally different. So are we going to create a model for each cell or what? Or we just introduce some randomness to the same model? In that way, I can account for the variation. So which one you prefer? I will prefer the latter because they're the same problem. Okay, the mechanism is the same. The variation is just due to the between subject variation. So I can use the same mechanistic model to model them, but I can add some randomness, right? In that way, I can account for the uncertainty. So that's the idea of stochastic modeling. Okay, I do stochastic modeling. Okay, I'm not an ODE guy. Okay, 100% ODE guy. Okay, so now I want to actually give you another example. Okay, so this is just a very typical SIR model. Okay, people use this to model the epidemics. Okay, so susceptible, infected, recovered, or removed. Okay, people also call this removed sometimes. If I do a stochastic model, I see this very interesting oscillations. Okay, and that actually means something, which means there's a cycle. Okay, from the burst of the disease to the eradication, right? So if I use ODE model, okay, you just get a flight tail, tells you nothing. The only interesting part will be just this beginning part, okay? So that's one example. If you don't use the static model, you get a totally wrong, okay, impression about the problem. Here I have randomness, I have noise, but I also see this prominent, oscillation. Okay, that oscillation actually is important for this problem. So that's why people actually use the stochastic simulation, okay, to mimic the system behavior, and the ultimate goal is to actually explore the possible outcomes. Okay, you can run the simulation multiple times and get a sample of all the possible outcomes. Then you will understand the distribution of this outcome, and that will tell you some useful information. Okay, so the key things in this kind of stochastic simulation is that random number generation and probability distribution. Random number generation, you remember, computer cannot actually generate true random numbers. Okay, computer just do what you tell it to do. Okay, so computer in nature is deterministic. So they cannot generate a true random number, but they can generate pseudo random number. Okay, so these pseudo random numbers actually can work well if the algorithm is well designed, so the period is long. When I talk about period, which means if you use a random number generator, for example, if you draw 1 million random numbers from this generator, it may start to repeat itself, okay, after each 1 million random numbers. So now this pattern will become predictable. Then it's not random anymore. Now people have designed generators that actually have an extremely long period. So for your research purpose, I think you don't need to worry about it, okay, because the period is too long. Okay, it's not 1 million. Actually, is I forgot. It's actually a huge number, like 10 to the power of 23 or even more than that. I think it's more than that. So usually in your simulation, you will not draw that many, random numbers, at one time. So the second thing is that you need to specify the distribution of the random variables, That is problem specific. So to generate the pseudo-random numbers, I will recommend this Mersenne twister generator. It has a very long period. And do not use the congruential generator. Although that's a very classical generator. Or the first generator you will learn in a computer science course. But the performance is pretty bad. And its period actually is short. It's just actually m. If you specify m beforehand, that becomes m. So the Mersenne twister actually generator, I always actually use it. In my own implementation. So far, I haven't tried other generators, although I read some papers that claim their generators are better than that one. Anyway, when you generate random numbers, you probably will use something called acceptance and rejection method. So the acceptance rejection method, the implementation of this method is simple. So I want my random variable. My random variable is x. I want to generate random numbers from the distribution of x. So this is a distribution. The blue curve. So what we do is actually generate a uniform random number v. Within a and b, and then I generate another uniformly distributed variable u. From 0 to c. C is actually greater than any constant. Any constant you can specify. That is greater than the maximum value of this curve. Above this curve. Any C. Once it's above the top of the curve, it can be used. Then, if this point, the pair of u and v, actually is a two-dimensional point. If this point falls under the curve, you accept it. If the u and v falls outside of or above this curve, you reject it. In this way, you will generate a random number. Follow this distribution. So I don't think I have time to talk about why is that. But simply speaking, this is the idea of acceptance and rejection method. And it works for arbitrary distribution. Now, this is a good thing about this method. Because there are many other generators that you need to know the mathematical details. For this one, you don't need to. You just need to know the distribution function. That's all. Then you can just use this method to generate random samples. It's gonna work. So another thing I have to mention is that the so-called SSA. Stochastic Simulation algorithm, and the concept is extremely simple. At each step, you draw two random numbers. So based on the first random number, you can determine which reaction will occur. It's like a lottery. So there's one reaction win the lottery, then it will occur. The second random number, you actually draw another random number to determine how much time the reaction will take. Then that's done. You just repeat these two steps, and that's called SSA. Extremely simple, right? So for example, at this step, it happens that the ninth reaction will occur. So the particle 3 and particle 100 will form particle 49. You get a complex. So you draw another random number, so to determine what's the time it needed to finish this reaction. Then after that, the number of particle 3 decreased by 1, the number of particle 100 decreased by 1, but the number of particle 49 increased by 1. So in other way, you simulate the changes in particle numbers. And here's the example. So here what I draw actually is total number. Okay, I start with many A and B particles. Okay, then I get a C particle, complex. So I think the number here, the color here is wrong. Okay, color here is wrong. The red actually is a C. Okay, the C actually will increase. So it's different from the color here. Okay, but here is consistent. Okay, but these two are not. But anyway, so C will increase, A and B will decrease. Okay, if you use a random simulation. And if I reduce the number of particles in a system, now you see what I mentioned this morning. Okay, so this curve looks pretty smooth. I can use ODE, right? I can also use ODE to model this one. But if I reduce the number down to like 5 or 6, now you see the curve just become stepwise. And now it will be a big problem if you still use ODE. Okay, approximation will be bad. So I think that's all I want to talk about today. And thank you. Do we have time for questions or any question? Okay.
When you're talking about that example with the number of different cells, the nature paper, so is it possible to, in stochastic modeling or stochastic method, to figure out, I know it's random, there are some places where it could be non-random. Like, for example, some of those cells could be going through cell division.
Yeah. So
you want to find those cells.
That's what I'm saying. I can use the same model to model all the cells, right? For example, I have the same model for all cells. However, my parameter, they are different for each cell, right? So the theta 1 corresponding to cell 1, theta 2 corresponding to cell 2. Then I have the same mechanism, but I have different parameter values for different subject. That's what actually I'm going to cover on Tuesday. It's called a mixed effect model. Okay. So this kind of model actually allows you to do this. Okay, use the same model for different subjects, but you can also account for the variation, okay, between subjects. Okay. Okay. Thanks.